Hello and welcome to our Chapter 1 Atoms discussion. We are going to end this chapter with a little bit from Chapter E, which is Section 6, based off of energy. Today our discussion will contain when we start to classify matter, what is matter. We can dive into a couple of definitions of atoms and molecules. We'll be able to look at the scientific approach of how historically we came to where we are today and value and appreciate the work that scientists have done before us. We'll be able to talk about what a scientific law is, some theories, and we'll get into a couple of experiments that scientists did to help us understand how do we have this picture of what an atom is. So what I want to start us off with is this idea that chemistry, which you all are studying in this class, is the study of matter. How does it react? What does it look like? Where do we see it in nature? And so the idea of matter itself is what we have to start to dive into. And so when we think about matter and atoms, we're going to start with a definition for matter. Anything that occupies space. That's the first criteria. It has to have some sort of a volume with it. With that, it needs to also have mass, right? So we can think about macroscopic world things, a cup, a desk, a computer. We can also think subatomic things, a proton, a neutron. There might be smaller. They might be difficult to see with our own human eyes, but they are still classified as matter, this overarching idea, the realm of what chemistry studies. And so it doesn't matter how big or how small, but as long as it occupies space and has mass, we get to study it in chemistry, and we get to see what it looks like, what does it do, and things like that. So matter is composed of particles. These are some definitions from our textbook. Why I like to do some PowerPoint slides with these is so that we get the definitions down quicker. You can look these up in your textbook. You can read them from the PowerPoint slides provided for you. So matter, we're going to start focusing on that subatomic realm. Yes, we like to think about the macroscopic worlds, cars and desks and things like that, but chemistry is really looking at how things react, and to understand how matter reacts, we need to look at the subatomic realm. And so looking at it from the particulate point of view, matter is composed of particles. Neutrons, protons, electrons, that's what we're going to see in this chapter. How did we discover them? It's very exciting to think about where we've come from. In the past 100 years, we've learned so much in chemistry. And so that's where we are going to start our story, our history, really, of chemistry. Now, we've probably heard this a lot before. Structure dictates function. We're going to dive into that a lot. If you're from the biological realm or anything in biology, biochemistry, molecular science, things like that, we always kind of hear this saying, the structure dictates function. How the particles get together is very important. So we're going to look at that throughout this whole semester course. We're going to see what is the structure of the molecule, how did those atoms come together to make that molecule, and we'll see how that is dependent on almost anything. I like this statement though right here. How the particles come together dictates the physical properties of matter. We'll try to relate all of these things to things that we see in the observable world. Sometimes we might not be able to get that far, but we can at least see some sort of experiments that help us dive into matter. There's our definition that we talked about. Matter is anything that has mass and occupies space. So it has a mass and it has a volume. And we as chemists, we seek to understand. And that is what we're here to really dive into, especially in this chapter. How did the chemists coming before us develop all of these principles and theories that we have to learn about? And so, again, a couple of definitions, I apologize, but when we look at and start to communicate these things in these chapters, we really want to make sure that we're using the correct terminology. So atoms, basic submicroscopic particles that constitute a fundamental building block of ordinary matter. What does that mean? They're atoms. They're going to be things like hydrogen, helium, oxygen, the atoms themselves, right? So we'll think about, once we get into what makes up an atom, we'll think about this as just being the one element off of the periodic table, right? When we think about atoms, we can think one representation of an element. So when we look at our trusty periodic table, we are going to be able to see one representation of that element is what we call an atom. Now, a molecule is something very, very different. Substance is formed when two or more atoms come together in a bond. And we're going to be diving into bonds a little bit later. Section 2 is, or unit 2 is when we're going to be able to dive into those. But a molecule has to be more than one atom, two or more. And so when we think about whether we have an atom or a molecule, that really determines what we're talking about. If I talk about an atom of oxygen, I'm thinking of just one basic atom, oxygen, just like what I wrote up here. Now, oxygen can form in what we call a diatomic molecule. And that is very different than plain old oxygen by itself as an atom. So actually, when we think about the term oxygen, the name of the element, it's not very descriptive. And so thinking about oxygen atom versus oxygen molecule is what we're going to dive into and see what do we mean when we see these two things. Which one do we find in nature, right? Oxygen can also form into O3, which is ozone, and that's what we have a big discussion of in environmental chemistry. Part of my background is environmental science. A lot of my undergrad research was in the global climate change. And so when we think about all of these different types of representations of an element, we have to be able to know what we're discussing, right? All right, with the classification of matter, it's really important for us to be able to talk again about not only the name of the element that we're talking about, what form it's in, whether it's an atom or a molecule, but also the state and the composition that it's in. The state is simply going to be whether it is a solid, liquid, or gas. Those will be our phases. Another word for state is a phase. And that's what we're going to be able to see. Composition. Now, a composition is going to be very specific. It's going to be the type of particles we see. Mainly with composition, we're going to be seeing, is it pure or is it a mixture? And then we can classify a little bit more with that. Overall, the state is something that I think we're all a little bit familiar with. The state of matter changes from solid to liquid to gas as we increase temperature. So if we think about a solid, I use this diagram, we can add heat to an ice cube and make it turn into liquid water. If we add heat to a liquid, we can turn it into a gas, like water vapor. So knowing when a substance, whether it's an atom or a molecule, knowing whether it's a solid, liquid, or gas in a reaction can help us truly understand how is it reacting. Solids are very tightly packed. We see all of these solids bunched up together. And when we think about that, the ones in the middle might not be able to reach something on the outside, and the ones on the outside are exposed, right? So solids react differently than, say, a liquid. A liquid is a little bit more spaced out, right? So when we think about that liquid, we can see some spaces throughout that substance. Things can come in between, the molecules move a bit more, and then we come to gases, which gases, what we'll see in chapter 10, a couple weeks away from now, but in chapter 10, we'll see that gases are so spread out that they literally take the shape of their container, right? So they spread out as much as they can. And one of our theories that we're going to talk about in chapter 10, the kinetic molecular theory, helps us understand that gases act almost independently of one another. Solids and liquids, they're kind of packed together. They interact. They do some more things together. But gases, they're off on their own, doing whatever they want, very independent. So I like this picture because not only can we start to see the particulate diagram right there with the packedness, but we can see that solids have a very concrete shape, right? And a concrete volume. Liquids tend to take the shape of their container, but they're at least a fixed volume. And gases just spread out as much as possible. So when we think about all of these states, we can see that it is overall 3 different types of matter. So even though we can think about an ice cube melting to become liquid and then boiling to become a gas, a vapor, the actual molecule H2O is the same, but the reactivity and the physical properties of those solid liquids and gases are important for us to be able to discuss. When we want to talk about composition of matter comes with a variety of subcategories. The first thing that we want to think about with composition is, do we have one type of atom or one type of molecule in our sample? And so we can have a pure sample or a mixture. Now, a pure sample can have a couple of different definitions. We're going to talk about 2 main ones. A pure sample being an element, or it can be a compound. Compound and molecule are very similar. We're going to call them the same right now, so you can interchange those. Once we get into the type of bonding that we'll see in chapter 3 and 4, that's when we'll get to have something more specific. But for an element, one type of atom. So this could be something like neon. If I have a vessel of neon, a lot of chemistry experiments use inert gases, gases that don't react. Argon is another example of that. So when we think about gas tanks, we can think about those elements being just the atom itself. Now with a compound, think about that as being the definition of a molecule, 2 or more atoms. So I'm going to write that, 2 or more atoms bonded together. We still only have one molecule or one compound in our sample. It's still a pure sample. But those atoms are bonded together. So a sample of carbon dioxide gas could be pure, it could just be carbon dioxide. However, it is a molecule itself. Same thing with a sample of water, H2O. Now, notice for none of these compositions of pure or mixture, we won't see the idea of solid, liquid, or gas, right? Phase or state is one way to classify matter. Composition is another way. So they can work hand in hand. We can say we have a pure sample of neon gas, but the pure sample dictates the composition. The gas would dictate the actual state or phase. A mixture can be a homogeneous mixture, or it can be a heterogeneous mixture. For a homogeneous mixture, it is thoroughly mixed. Again, 2 or more compounds or 2 or more atoms not bonded. A mixture would be something that is like salt water. Salt water is a mixture of sodium chloride and H2O. Those aren't bonded together, but they are mixed thoroughly. We can think about the air. The air we breathe is partly oxygen gas, it's partly nitrogen gas, it's got some carbon dioxide in it. We have a little bit of helium and hydrogen floating out around there. So it's a mixture, but again, it's thoroughly mixed. We won't see things that we could pick out, right? A macroscopic world idea would be something like tea, or if you add things to your coffee. I like my coffee with a little bit of milk and a little bit of sugar, and I stir it up and it becomes a homogeneous mixture. I can't just take a sip and say, oh, that one was just the milk, or take a sip and be like, oh, that one was just sugar. It's all of it together, combined and thoroughly mixed. Heterogeneous, on the other hand, is not thoroughly mixed. So we get kind of like this cookie cutter, this side is more one thing and this side is more the other. The best thing that I can think about in a scientific example is the ocean. A lot of my undergrad research back in the day, a long time ago, was on the top 6 inches of the ocean. We see a lot of dissolved organic matter. We call it chromophoric dissolved organic matter. And this is mainly from plant runoff. It's a lot of issues with the degradation of soil and the degradation of plants. And then it gets into the ocean. And that dissolved organic matter can react with the sunlight to make small molecules that then go contribute to climate change. So the top of the ocean is quite different than the bottom of the ocean. And so we can think about that idea of the ocean is not a perfectly thorough mixed thing. Our ocean, closer to Orange, is Huntington Beach and Newport, which is quite different if we decide to go down to San Diego and hop in the ocean down there. Another example, trail mix. I'm a big camper and hiker. My family loves to go camping and hiking, and so we like to make snacks on the road, right? And trail mix is a great example of a heterogeneous mixture. When you think about all the things that you can put in it, whether it's dried cranberries or dried blueberries, you can have some cashews in there, or almonds. Sometimes if you're like my mom, you put M&Ms in there. And if you're my son, you eat the M&Ms first because you can pick out the M&Ms. It's a heterogeneous mixture. It's not thoroughly mixed. Those are all great examples of how to decide the composition of matter. This chart is in your textbook. It's an awesome chart to be able to just look through some questions to ask yourself, just to decide elements, compounds, mixtures, and things like that. I like the particulate diagrams as well when we're looking at your textbook. Has beautiful, beautiful particulate drawings.